Preamble, let me thank those of you I've worked with. Mike Peretz is here. He's given me a lot of feedback, constructive criticism on documentation in particular, which in turn inspired me to write a spectral decomposition algorithm that was outside of I'm sorry, I said spectral decomposition algorithm, a spectral balancing algorithm that was much simpler and much faster than running all the spectral decomposition stuff. Mathematics is the same. You're going to get the same answer either way, except one runs about 10 times faster, doesn't have all those intermediate volumes. So thanks. Jason Grumble, another fellow, and he works at, what's the company name again? Ancora. And so he's given a lot of feedback as well on spectral decomposition, spectral balancing. So keep giving feedback, pushback. You see something that's unclear. There's a lot of stuff that's unclear in the documentation because there might be 5,000 to 10,000 pages in the documentation. So we'll just fix it. Okay.
You have to use the mouse.
I hate that.
I know.
Okay, so now I click it and nothing happens. So what? Scroll down. What is this? It sucks getting old, by the way. Oh, now I just hit that. Oh, so I have to hit it really hard so the electrons move faster? Oh, you moved the right one instead of the down one.
Both work.
Oh, now it's working. Okay, here's an outline. Why are we interested in low frequencies? Data quality problems with low frequencies. Some hysterical work that I learned from my buddy Chopra. AASPI implementation. A couple of applications. Not as many as I could do, but a couple. And then some spectral balancing and coherence, some features that Pamela found that were, oh, that's interesting. Didn't know that. Okay, so here's the value of low frequencies and kind of a common workflow, let's say for model-driven inversion, where you take your horizon picks, impedance from your well logs, do some kriging in between, interpolation to build a background model. Then you'll run, here's your model impedance. Then you're going to hit a low pass filter on it, let's say 0 to 10 hertz, 0 to 15 hertz. That's your low frequency impedance estimate. You take your seismic amplitude, might go from 10 hertz to 80 hertz. You're going to generate synthetics at the well, get a source wavelet. The source wavelet does spectral balancing, okay? Because that's what inversion does. You're going to get an impedance inversion from, let's say, 10 to 80 hertz. And you're going to put these two together, and there's your broadband impedance, okay? So this is almost all the commercial software does this. There's 4 or 5 companies that do this. Okay, now the problem with low frequencies, when you're retired, you have to have a ranch with cows on it. And then one day these trucks showed up because I'm over the Blanchard survey. And I learned that a problem with the ground force with vibrators is the ground force is proportional to the reaction mass and the distance that the mass moves, and the second power of frequencies. So if you go from 10 hertz to 5 hertz, because you're squaring it, you only have 1/4 of the power of force going in, okay? So we tend to have lower amplitudes at the lower frequencies. Could make the trucks bigger, but guys like me won't like that because you leave big holes in the ground as you drive around. Bad enough with the fences. Then the solutions are you can have longer low frequency sweeps, really commonly done today. Improve vibrator mechanics. There's some really cool papers on that as well that get around the reaction mass problem. And then several of the companies, they go back to what I did at Amoco. Not I did, but my colleagues at Amoco did. You'd have shake tables and figure out what the response of the geophones is at 2 and 4 and 5 hertz. Correct those deterministically, and then that gets you close enough so deconvolution can get you into the right area. Okay, now we also have ground roll. So this part of the curve is your normal reflectivity, and this low frequency area, that's your ground roll, you know, Rayleigh waves, things like that. And we also have migration aliasing artifacts, steeply dipping events. And the solution to that is basically denser sampling. 55-meter bin spaces, things of that nature, independent geophones versus groups. All of this requires more modern data. And I would say if you're going to collect data, collect it right. I mean, that's obviously what you want to do. But we have a lot of old data. So what do we do? Here's some of that historical work. And my buddy Chopra, I'm going to market our book. Hopefully it'll come out in October. Chopra and Marford, Attribute, blah, 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 volume 1. And as we're writing the book, and then he came up with a question, hey, can we do this? And it's a paper in 2002 that I had missed by some folks at BP. And they had a thing called frequency slice filtering, okay? And just to say what they're doing, they're have a filtering process where they maintain the low frequency data. They're able to gut out the cross-cutting noise and the low frequencies so they can use it. It's BP. They like elastic impedance inversion. And here they show the red curves are when you use the low frequencies, and the blue is you use the low frequencies with the noise in it. Okay, so that doesn't work as well. Yes, sir.
Why not that question?
Why not?
So, is the context here post-stack data?
This is post-stack here. Yeah, for this example. Yeah. And I think everything can be done pre-stack as well. I don't see why not. So back again to this Hodgson and her colleagues, Paul Garasino, another Amico guy, he was the one who actually did the filtering technique. And what they would do is they would take a Fourier transform. So basically every 0.25 milliseconds, I'm sorry, 0.25 hertz would be their sample increment. And so the 0 to 6 hertz, 24 frequencies, they'd use a filter size of 237 by 237 meters, okay? And then you go to 10 to 12 hertz, so that's maybe 8 frequencies, 87.5 by 87.5. So this is probably 25 by 25 meter bin, just thinking, or maybe 12.5 by 12.5. So they're using different frequency different mean filters for the lower frequencies. They're going to use a bigger filter. Now, it's done in a frequency domain, so there's two problems. One, if you're a normal person, I'm not even normal. I have no idea what I'm doing if I do a mean filter in a frequency domain until I transfer them all the way back. Two, you're going to put in, let's say, if you have n samples, you're going to use 1 over n amplitudes. Those are real numbers. I'm not changing the phase, which means I'm always smoothing horizontally, and I'm not smoothing according to data. But at the end of the day, here's their impedance inversion on the left of the original data, and here's their elastic impedance inversion on the right. And you can see all of this garbage is gone, okay? So that's the goal. Here's another paper that I was familiar with. In 2009, we put this in the SOF 3D program, but they didn't do it the way Helmore really intended, because I didn't read the paper right. Here's his data, original, and then he does a similar workflow that Hodgson and her colleagues did, except instead of doing it in the frequency domain per se, he ran a bunch of filter banks. This is exactly what I'll show you in a bit. So we'll have a 0 to 5 hertz, let's say a 0 to 10 hertz filter bank centered on 5, a 5 to 15 hertz filter banks centered on 10. Those data are going to look like seismic data. We're going to apply, it's just bandpass filter data. We're going to apply structure warning filtering to that. And what Helmore did, he used big filters for the low frequencies and short filters or no filters for the high frequencies. And he got this fluid impedance estimate down on the bottom from 3 to 50 hertz. That quite nice. Okay, so here's what we did in AASPI. It's all on our website. The old website that still works, not the 4 years conversation from OUIT about the new website we're going to roll out. Yep, me and Doubting Thomas. So it's in there, and it'll be under the post-doc data conditioning, okay? And this is where it is on the main GUI, the AASPI util GUI, under data conditioning, spectral balance, the program I talked earlier about that Mike Hertz got me initiated on. SOF 3D, it's in 2 places. And then these 3 new programs that I'll describe. So here are the 3 new programs: generate bandpass filtered volumes, filter those volumes, the ones you want to, put them back together, and then let's do some spectral balancing after it. Okay, so there's 4 programs. You would run them one at a time. And so here's the first one, very, very simple. Here's my seismic amplitude. Going to have low frequency volume 1, 2, 3, or N, and then a high frequency volume. In this case here, I'm going to have one centered at 0, 5, 10, 15, 20, and then everything else, 25 above. Okay. This one I'm not going to filter at all. I'm just going to leave it alone. This one I'm actually going to throw away. There's almost nothing that's centered around 0 hertz that's useful. But this one's quite good. The one at 5 hertz tends to have a lot of data in it. So we've got the GUI in here, and you define, 5 to 20 every 5 hertz. And it's going to output these bandpass filtered volumes. The second program is the one that mimics those 2 papers I referred to. And so in this example, I'll use a 5, 10, 15, 20 hertz. 2 key filters, just the same thing, raised cosine filters, overlapping, recreate the data. The data in this case were 25 by 25 meter. I'm going to be more aggressive than normal SOF. I'm going to use a 50 meter at 20 hertz. Well, my wavelengths are twice as long. At 10 hertz, I'm going to use 100 meter, 4 times as long. And at 5 hertz, I'm going to use 200 meters. So it runs a little slower, okay? And then in between is 75 hertz. So that's where this is. I put in these low frequency volumes, and the GUI is such that you select those, tell it what, you fill out this little table, and then it runs, okay? What does it run? It runs program SOF 3D, but you don't have to fill out all the parameters. It's using some default parameters. You'll get the mean filtered volumes and the mean filtered noise, okay? Okay, then the third one, yes, sir.
Edge preservation.
Off. Because for the low frequencies, the edge preservation is going to enhance those low frequency edges. So this is, again, one of the tricks that I picked up reading those papers more carefully. So here is the philosophy and hypothesis is I'm going to hammer those low frequencies. I'm going to lose some edges. Now I can do a median filter, and that'll be a little better. And I'm hoping, but it's faith-based processing. Okay, but you're comfortable, right? 20 to 100 hertz, that'll have plenty of definition of the edges in it. But that's just faith, okay? But no, you don't want to do edge preservation for the low frequencies because that actually will hurt you. So here's my mean filtered volumes, the ones I did, let's say 3 or 4 of them. Here's a couple I looked at and said, I'm okay with that. I'm not going to mess with it. And then this high frequency volume in this last case was 25 to 120 hertz. Okay, so I'm going to look at suppression of low frequency noise and then separation of low frequency signal. And then there's an application where, it doesn't do a heck of a lot of anything. I don't have a lot of low frequency noise in the data, and it didn't do anything. It didn't hurt the data. It just used up my time. Okay, so this is Parihaka 3D, one of the New Zealand data sets. You wonder, why would these guys show in New Zealand data sets? Because the data we can get, if you give us your data, we'll work on your data. But that's the way it is. Okay, let's run aggressive spectral balancing, going from 0 to 125 hertz. Hey, looks pretty good. If you looked at this in detail, and you'll have access to this, you can see, yeah, I get a lot more higher resolution in the data. But then where I have these yellow arrows down here, you see I got this steeply dipping noise. So let's run this workflow. I got the high resolution, but I got rid of the steeply dipping noise. Okay. Let's look at the 5 hertz component of the original data, so you can output these, okay? And here's the 5 hertz component. So it's a Tukey filter that goes 0, peaked at 5, back to 0 at 10. Okay, very simple filter, raised cosine filter. And here's the noise. There's a little bit of noise up here. And then here is what we get out after filtering. And I think you'll agree, hey, we can use this last one for inversion. I'm showing all the stratigraphic stuff just fine, okay? Then here's the 10. Here's the 5 hertz noise. Subtract one from the other. This is what I threw away. Yeah, I'm comfortable throwing that away. Then here's the 10 hertz component. So it goes from 5, peaks at 10, to 0 at 15. And yeah, there's some noise down in here. And then filter it. Okay, helps a little bit. And then here's the noise I threw away. Maybe I'm getting rid of some dipping reflectors here, but it's still pretty strong, not too bad. Okay, and then here's the average time variance spectra of the original data. And you can see there's very little amplitude at the lower frequencies. This reads 20 right here, so 10 is about here. And then after spectral balancing, you can see I have a lot of the low frequencies back in there. Also some of the high frequencies. Okay, so now yesterday, my buddy Chopra, we finally got all the well logs and the horizons and stuff like that. And he did an impedance inversion. And on the left is kind of a traditional workflow. You look at the data, you see where the signal are good. And so he built a low frequency model by using the well. In this case, we only have one well at this time, but we got an impedance log. Use that to generate the background. Use this horizon up here, this horizon here, this horizon there. They're from Pierre Caram, now at Devon. And so we use those horizons. And then he did an impedance inversion of the seismic data from 10, 15 up to 80. Put the two together. Okay, so this is conventional kind of thing you would do in, let's say, Hanson Russell or Jason. And in this one, we went down to 5 hertz. And now the background model is 0, 2.5 hertz. It's bent down a little bit. So very, very little background model now. And the one difference is because we have spectral balancing and we have a little higher resolution. Though when you have a wavelet, remember, when you divide by the wavelet, you're still doing spectral balancing in inversion, okay? And this one has a little better tie because we're using the low frequency model at the well log to generate the low frequency model at the well log, like duh. And here we're using the seismic data. So that's encouraging, okay? We need another well to validate. Okay, here's application 2, Great South Basin. A lot of faults. Let's apply 5 to 120 hertz spectral balancing of the original data. Okay, yeah, I got some low frequency stuff I don't like, but other than that, it looks pretty good. A lot of improvement in resolution. Here is, let me do the low frequency structure running filtering. Okay, I get rid of some of those artifacts. I also seem to get rid of the fault plane reflectors. Notice I don't have any fault plane reflectors on the original data. So this one kind of surprised me. Here's the 5 hertz component. Here is the smooth data. Hey, pretty good. I'm comfortable using that for inversion. Here's what I threw away. Okay. Data were 12.5 by 25 meter bins, 200 meter radius for the lowest frequency. And then here's the 10 hertz component, similar thing, steeply dipping stuff, throw away. That's my noise, right? Except not noise. So I take my low frequency filter data, put it all back together, take my 5 and 10 hertz guys that I rejected, put them together. I scale each one independently, statistically, a couple of standard deviations. And then I overplot the noise and red, blue, and the regular seismic, filtered seismic in gray. And what you see is, oh, this has got all the salt plane reflectors. So I'm going to ask Michael here. There was a paper back 25 years ago where people enhanced fault plane reflectors using dip, and I can't find it. My memory's not good enough. So if anybody remembers that, I'd like to know it. Okay, here's the time slice through the filtered signal. And then, yeah, fault plane reflectors. Kind of interesting, It's not an attribute, but it's interesting. And then here is the spectral balancing, just like before, with the before and after. Okay, so I'm going to finish up with in this book that Chopra and I are writing, we're adding a pitfall in every section. People like the pitfalls better than the super cool examples, okay? Because pitfalls is what you usually get. And so spectral balancing and coherence, improved edge delineation, and my buddy Chopra in APG Explorer, you know, in the geophysical corner, he always shows dynamite pictures, knock your sock off, okay? Well, I would say in most cases, we don't get any change. And then working with Pamela, she found one like, hey, what the heck's going on? My stratigraphic edges are disappearing after spectral balancing, which is annoying. So here's one where it doesn't make a lot of difference. It's the Cora 3D, another New Zealand survey. I've got a seamount in the middle, got a turbidite here. I have a turbidite there. Here's on the original data. We do spectral balancing, helps the vertical resolution a lot. But in terms of coherence, not too much. If you think of coherence, think of cross-correlation. I take the traces, I cross-correlate. I normalize by the autocorrelations. The wavelet is kind of taken out in both cases, okay? So all it really does is weight discontinuities at the edges a little more. Doesn't really change the algorithm. Then here's her data set, Gulf of Mexico merge survey, the one next to Georgenis there on the wall. Here's before and after balancing, and okay, yeah, this little meandering feature comes in a little better. This guy comes in better, and these guys are weaker. So here's her vertical data. Then after spectral balancing, now we can start to see some of these lateral changes. Here's her original frequency, peaked at about 35 hertz. And then the spectrum after spectral balancing is it's not quite flat because it's a merged survey, and one of her headaches is they have different spectra on each side, so it doesn't make it perfectly flat. It compromises, and you can talk to her at a break about that. Okay, a little blow up. So here, this little channel and this channel and this channel, well, or let's just call them edges, they're gone. So what happened? Well, here's what we have. In the original data is tuned at 35 hertz. And so if I look at coherence plotted against CMY, then you can see, oh, this guy is at kind of tuned at 35 hertz, this edge, this one's tuned at 20 hertz. So the coherence she ran originally was run on a tuned volume. And then when I spectrally balanced, it wasn't tuned. So this is what we do with multispectral coherence. We realize that, you know, if I happen to have reflectors that line up like my fingers across a fault, I don't see that. But if I change the phases and the frequencies, well, then they do start. I can't make my fingers skinnier, but anyhow, they don't line up anymore. So that's exactly what she's seeing. So she got lucky with the original data. She's seeing things that are tuned in because her data are tuned, spectrally balanced. Well, they kind of go away a little bit. Okay, so in summary, we've established or distributed a workflow that can help suppress steeply dipping low frequency noise, steeply dipping low frequency stuff, okay? Spectrally balancing such filtered data increases the contribution of the low frequency part of the data for use in impedance inversion. Otherwise, you have to kind of throw it away if it's contaminated. Not all steeply dipping low frequency features are noise. I showed you fault plane reflectors. And then if you have depth migrated data, you're going to have steep dips. And then spectrally balancing the data can remove coherence anomalies that were fortuitously tuned by the original unbalanced data. So, any pushback?